How does that work?
All right, let's get started, guys. Our first presenter is Bogdan Pinte. Bogdan received his BS degree in electrical engineering from the University of Illinois at Urbana-Champaign in May 2013. He's currently pursuing a Master's of Science degree in electrical engineering at UIUC and working under Professor Peter Sauer. His work focuses on working with a team of researchers to develop a phasor measurement unit with an end goal of deploying a network of PMUs across the Champaign-Urbana area.
Okay. I'm gonna have a lot of notes on here, like on future slides. Is it okay if we can just like minimize this a little bit? Like make it smaller? Yeah, it's perfect. Okay. So my presentation is gonna be about constructing a phasor measurement unit at Illinois. So I work with Mike, Kenta, who's gonna present next, Andy, and we work with Carl Reinhardt under Professor Sauer. We also receive funding and guidance from Professor Overby. So in this presentation, I will give an introduction of what a PMU is, how the data is used, and why it's an important device in measuring the system of the power grid. I will talk about the objectives, design of our PMU, what results we get, and how much it costs, and how it compares to other PMUs.
That's an interesting way to give the outline.
Yes.
You're not a normal person. It's an LAS thing to do.
So in an introduction, PMUs, they're considered one of the most important measuring devices in the future of power systems. The reason being is that they allow you to monitor the state of the power grid in real time. For example, there was a blackout in 1996 in August, and the graph on the bottom, the graph on top, the red sine wave kind of looking graph, that shows how the grid behaved in real time and what actually happened. And when they did a post blackout analysis, they gathered a bunch of data and they put it into their model, and the model gave this output of the power grid. So that means the model was not good. So PMUs allow you to build better models, so you have a better understanding of how the grid behaves. And this is because system operators, they use models to predict how the grid is going to behave tomorrow, for example. So models are very useful. Also, there was a blackout in 2003, and from what I hear, there were conditions. Basically, the power grid started to go bad a couple of hours, from what I hear, before the blackout actually happened. And if they had real-time data, they would have been able to look at the power grid in real time and see, kind of know what's going to happen in the future. But that was not the case because they didn't have enough real-time measurements.
You know what that COI stands for?
I do not know. It's somewhere in the Western Interconnect. Colorado, something.
Close.
California.
Closer.
I don't know. My two choices are up.
That's not center of inertia, which is what the average power engineer would assume. California, Oregon, intertime.
Okay.
It's
Yeah.
It's the tie line from Los Angeles to Oregon.
Mm-hmm. Yeah, it's from the 1996 blackout. That's where it happened. So how does the PMU works? Like I said before, the power of the phasor measurement unit is in its ability to measure, to take synchronized measurements. For example, if you have two PMUs, this shows the Eastern Interconnect, one in Florida, the other one up there in the north, or wherever that is. If you look at those two data points that the PMU gathers, you are sure that those measurements were taken at the exact same time with an error of 1 microsecond. And that error of 1 microsecond comes from the GPS, because the GPS is designed in such a way that it's accurate to any other GPS in the world to within 1 microsecond. So that's as best as data can be gathered. That's the error in the data. So what do we get from these measurements? Well, we look at the voltage magnitude, which indicates losses in the system. We look at the frequency. The frequency shows instability. So for example, if your frequency is higher than 60 hertz, that means there's more power being generated than being produced, which is not good. If your frequency is lower than 60 hertz, that means there are more loads in the system than you have power being generated. Again, that's not good, because you might have a blackout in the near future.
What do you mean by magnitude losses?
Like if you look at a transmission line, for example, you measure the magnitude of the voltage at one point, and then you measure the magnitude down the line, then if there's power being lost, then the voltage magnitude decreases. That's my assumption. Also, the phase indicates the direction of power flow. So in these two cases, the phase in Florida is greater. The phase is the distance between the vertical dotted red line and the beginning of the cycle, or the beginning of the sine wave. So if the phase is greater in this picture than over there, that means the power flows upwards. That's basically phase dictates the way the power flows. As a side note, the reactive power flows as a function of voltage difference. So usually you want your voltage profile to be flat, which means that you can't really transfer or transmit reactive power. That's why you have to inject reactive power locally and at different points. This table illustrates the difference between current PMUs and our PMU. Current PMUs, they range between $10,000 and $15,000, and our PMU was designed to be around $1,000. The main difference being that our PMU samples one-phase voltages, as opposed to current PMUs, they sample three-phase voltage and currents. Also, current PMUs are incorporated into protective relays and other devices that are installed at substations, while ours is a standalone product, and it's installed in selected households. The objectives of the project is to use the GPS timestamp to get the UTC time to stamp our data. That's how we synchronize our data. We sample the wall voltage at a frequency of 10,000 hertz, so we take 10,000 samples a second, and we report at 10 hertz, which means every second we break the voltage wave into 10 different segments, and in each of those segments we calculate the voltage magnitude, phase, and frequency, and we store that data. We store it internally on the PMU, and then every hour we upload the data from the PMU to a web server. And we also have a UPS that backs up our PMU in case there's a blackout. There's important data to be gathered during those times. So we want to be able to analyze that data later and see exactly what happened when there's a blackout, or when that transition happens between normal operation and blackout. As far as hardware goes, we're using National Instruments hardware. We're using the SBREO 9632. And we're also using we have a GPS receiver and UPS and an AC to DC converter. And as far as software goes, we use National Instruments LabVIEW with FPGA and real-time modules. From my experience, LabVIEW is a visual programming language, but it's a little bit more difficult to implement very complex logic, unless you know what you're doing. So this is the
The UPS is the uninterruptible power supply?
right. Yeah, that's what it stands for.
Okay, so you don't need the grid.
You don't need the grid when there's a blackout. You can just get power, and this is what the design shows. Um, during normal operation, you would have power. That's so during normal operation, there's a voltage coming from the grid that powers our UPS, and in turn we get power to the SB reel, and also we use a voltage divider to step down the wall voltage so that we can read it using the SB reel, because the SB reel has maximum voltage input of 10 volts. So we have to step down the grid voltage to a maximum amplitude of 10 volts. And then we also get GPS timestamp in our data, and then we upload that data to a web server. Now, when there's a blackout, uh, there's no more voltage at the wall outlet, and the web server is out. But that's okay because we have the UPS to back up our PMU, so we are still able to process what's happening at the grid through the voltage divider and store all that data internally until the power becomes available. Then we upload the data to the web server. So this is the data that we take from the GPS. There are many different data that can be taken from the GPS, such as how many satellites are in view, the elevation of satellites, the Earth's magnetic variation. But we only look at the time, date, and we look at the second pulse, because the GPS outputs a rising edge, has a rising edge at the beginning of each second, and that's displayed in that graph over there. So we know when there's a rising edge, the beginning, the second just started, and that's accurate to within 1 microsecond. Okay, so I'm going to explain. I'm going to talk a little bit about the code. Using basically we have two different files that we code in. One is the FPGA VI, and then we also have the real-time controller VI. The FPGA VI is just a file that tells the board to sample voltage at a rate of 10,000 hertz and writes all the data into a FIFO. It just blindly does that. The real-time controller, on the other hand, it is like the brain of the board. It looks at all the data from the FIFO. It timestamps it using the GPS time. Yeah, it calculates all the voltage magnitudes, phase, and frequency, and it uploads, creates a new file every hour to upload to the web server. This is the FPGA VI. It just basically shows you how the VI looks. What it does is just takes 10,000 samples a second. Here's a real-time controller. What it does is it waits for there to be a second pulse, so we know the GPS is working, and we can timestamp the data now with the time that we get from the GPS. So, like I said before,
How often does the timing come?
it comes every second. That's
Every second.
right. Yeah, we look at the rising edge of a second, and then we add. So whenever that happens, we add a tenth of a second to that. So we get 10 samples per second of data being outputted. So we sample at 10,000 hertz, and we report at 10 hertz. So that means every 1,000 sample points, we extract the data, and then we calculate the voltage magnitude, amplitude, and frequency, and then we use a timestamp to stamp our data. So this happens at 10 times a second. This is the code for the GPS that we only look at the time. We don't worry about position. This is the web server upload code, just to give you a feeling of LabVIEW. And like I said before, we have to step down our voltage from the wall to the analog inputs of the SB reel. And in order to do that, we have to decide whether we should use transformer or resistors. But since the key idea here is to reduce the cost as much as possible, we decided to use resistors. So if we use big values for resistors, we only lose about 1.63 millivolts or milliwatts, I mean, which is not bad. So we use resistors. It's also cheap. This is our power supply, the CP350S LG. That's the UPS that we're using. I mean not yeah. So this is retrieved from the data sheet, and it shows how much load it can run for how long. And our PMU consumes at most 15 watts, which means this UPS will be able to power it for 75 minutes during a blackout. This shows how the UPS operates. It works on a standby topology, which we later found out is not good for us because we don't want to be any switching involved. And the switching comes from the fact that during a normal operation, you have voltage being transferred directly from the grid to our power supply, which supplies our PMU. But when there's a blackout, there's a switching involved, which now it gets power from the inverter or from the battery through the inverter, and that switching is not good. We want to get rid of that, so we have to redesign the UPS. Um, and the voltage wave shows how the UPS outputs the voltage. I guess it's a simulated sine wave, what they call it. So it's not a perfect sine wave like you would expect at the outlet. So what happens during a blackout? During a blackout, the internal storage of the board is big enough, as 256 megabytes of storage, and our data corresponds to about 67.2 megabytes of data per day. So we can store 3.8 days of data. We can store 3.8 days of data on the PMU, but we don't need that because we upload it every hour. And the way we connect to our web server is using FTP, which stands for File Transfer Protocol. Initially, we had a server set up that we connected using SFTP, which stands for Secure File Transfer Protocol, but it's harder to implement in LabVIEW. Actually, you can do it in LabVIEW, that's from what I heard. So we decided to use a less secure connection type method. But we also the way this works is that both the server and the PMU have to be on the same subnetwork. So right now they're both in our lab and they work fine. You can transfer data from the PMU to our web server. But if for example, if I were to take the PMU in Urbana somewhere and plug it in, it's not going to be able to connect to the web server because the web server is on the school's network. So we kind of have to deal with that when we want to deploy units all over the area. So now I'm going to talk about the results. But before, this is the theory of what we should expect. You have this voltage wave, and we expect, in this case, the frequency is higher than 60 hertz. So we expect to see the phase increasing. The phase increases because the 60 hertz is actually higher than 60 hertz. So the 60 cycles happen faster than a second. So the phase should increase. And this is the data that we get. We see that in our case, the frequency is lower than 60 hertz, which means the phase should be decreasing, and it actually does. We also see that there are 10 lines of data per second, so that's what we also expect. And it's interesting to see that the voltage is 125 volts RMS as opposed to 120, which that's what we would expect. But the national code says that you can have between 114 and 126 volts, so it's within that range. No, it was here in Everett.
I replaced 2 bulbs today. It really irritated me. 2 flood lamps.
Dustin Ray's got all your data, so we're waiting for the report.
Yeah, I even had to buy a CFL. I couldn't buy a regular one.
You know what I find really fascinating?
Yes.
This has been borne out in research. Is that you look at the frequency. The frequency is 1/1000th of a hertz different than 60, and the effect that has on the changing phase. And that can be pretty dramatic when you're actually computing or working with large volumes of data, because the phase changes much more rapidly than your intuition initially says.
Right. And this is a visual representation of what our data looks like. So in this case, the frequency is higher than 60 hertz, which means that 6 cycles happen in less than a tenth of a second. In this case, 0.09976 of a second. And the phase, because of that, the phase increases, which is exactly what we expect to happen. As far as cost goes, our total cost comes to be about $1,100. That's because the SBRIO is pricey. We're trying to use the National Instruments MyRIO, which is a new device that they came out with, and it's supposed to be around $150 to $200. So that's going to majorly reduce our price.
Of course, we're betting on the come because National Instruments hasn't even officially released that device.
Right. Yeah. Some key ideas to remember that PMU data is used to basically look at the power grid in real time, and you can use all the data to have a post blackout disturbance analysis. Okay, this is the end of my presentation. Any questions? Yes.
Yeah, I have 2 questions. The first is, this is a very interesting presentation format. What is this? Is
This is me trying to get a new system to work, and then all the bugs on that yet. Maybe next week it'll be done.
No, actually,
that's
I
great.
think that this presentation
I think this is the presenter's monitor, and this is supposed to be what's on that monitor, but it's.
But as a guy that's actually receiving the presentation,
Right.
I like this interface because, I see what's coming up. And I can see his speaker splits. And
I didn't see that.
I like it. Okay, so now the real question. Go back to your slide where you were talking about the power and the resistors.
This one.
That one. And just because I know what happened, you learned a very painful lesson with this. Could you describe what happened?
Yes. So over the summer, I was trying to use a voltage divider to step down the outlet voltage, which is 120. Well, maximum of it can be, the amplitude can be 180 volts, I think, to 10 volts maximum for the SBRIO. And somehow the voltage divider didn't work because I didn't pay attention, and I put 120 volts RMS straight at the analog inputs, and that fried the board, and we had to get it replaced, and we just got it back like 2 or 3 weeks ago. So it's, you have to be careful with these kinds of situations.
Now, kind of my point with that is that this is something, as a given presentations in the lab, is you have very expensive equipment in this room, and you can blow up an oscilloscope doing the same thing. Particularly for those of you that are newer, that's why you got people like Kevin over here, and you've got a bunch of really experienced PAs that know what's going on. Don't be afraid to ask questions. Try not to blow up your equipment. And we did blow up a $1,000 board. The good news was they covered it in warranty, so we lost. Well, I don't know. He worked it, so. But we what we did is we lost 6 weeks.
Right.
So.
Precious time. Any other questions? Yes.
So your board, assuming you're using this new device, is now going to be like $200-300. And so, what do I gain from besides? So if I were to go out and buy a commercial PMU, besides the fact that it's 3-phase, but then I could just use 3 of your devices, what do I gain from paying the extra order of magnitude of cost?
I don't think you pay more. I think you pay less because our device is cheaper.
No. So like, how, or in other words, how are you able to make your device cheaper? Like, did you have to make certain trade-offs compared to, like the commercial PMUs?
Commercial PMUs are integrated in relays and other protected devices, so they don't just come as standalone products. They have other devices incorporated into a big unit. So that's why we don't have any other device with it. It's just the PMU by itself. But there's the FNAT out there, who's kind of similar. That's about the same price.
Wait, the FNet cost us $2,500.
Well then.
Are you guys getting phase angle good on this?
Yeah, we haven't really tested it yet to see if it complies to IEEE standards, but that's a future goal.
But that's been one of our objectives, is I think it's ridiculous for something as simple as this to cost $4,500. And if the monorail pans out as a simple device to purchase, and since we can use LabVIEW to generate the software, then we could turn it into a product and we could sell it. Now, we need a bit more sophistication, but one of the long-term objectives with this is Elu, who is Dr. Elu in Tennessee, that's running this, says, hey, we need to improve the quality of our PMUs in terms of what they deliver and information. And we set our sights on that next generation of PMU, hopefully at a reduced cost in terms of device and better capability. Also, a side note on the PMUs, I was kind of curious. There are two classes of PMUs, and I was questioning who's the fellow in Texas. He's from Serbia. Kuzunovic. And I said, so why are these two standards? And he said, well, there were two legacy devices that we wanted to incorporate into a PMU, and we didn't want to have people rewrite their algorithms from those to have to build a PMU. So to me, what that says is there's an opportunity to rewrite the world and meet the standard because you're not burdened by algorithms that somebody generated 20 years ago. So it's an opportunity.
Any other questions?
I mean, if you can make these inexpensively, we'll buy a lot from
That's great.
whatever.
Yeah.
But yeah, and it's not to critique FNAP because FNAP was designed for one purpose, and we're designing them for a different purpose, which is to gauge distribution voltages during quality. So FNAP wasn't designed for that. So I'm not critiquing FNAP, but if you can make a device that's similar, better functionality for 1/10 the cost, well, that's not bad. Yeah.
Okay. Thank you.
Test, test, test.
All right, our second speaker is Kenta Kirihara. He is in the process of finishing his BS degree in ECE at the University of Illinois. His expected graduation is in December of this year. His work is under synchrophaser data quality under Carl Reinhardt and Professor Peter Sauer, and his work focuses on working with a team to deploy distribution-level PMUs to find a better understanding of the grid and the problems associated with the usage.
Test, test, test. All right, just making sure. All right, so. Sorry. All right. So this summer, I was at ATC, American Transmission Company, right by Madison, Wisconsin, working on a PMU project up there. It's a DOE-sponsored project for the smart grid. Bogdan went over briefly about what a PMU is, so I don't think I need to go too much into details about what a PMU does, but we'll cover that later. So first of all, I'd like to go over the objectives of this presentation. I want to talk about how to analyze PMU data. There's two ways to analyze it. You can do it post-event, meaning after something occurs, you analyze it a day later or hours later. and there's real time when you look at it right away. And I also want to talk about possible problems associated with PMU usage. As an aside, I'd like to talk about working in the power industry as well, because it was a valuable experience. So, moving right along. What is a PMU? A PMU, as Bogdan already presented, is a device that monitors the state of the power grid. It's almost like a heart monitor for the grid as you look at pulses and phase and whatnot. Synchrophaser, you heard this word around everywhere within the presentation. It is the measurement the PMU takes. It is the voltage magnitude, voltage angle, voltage frequency, and current magnitude. However, the current magnitude is not always there. It depends on the vendor. So in the PMU that I've worked on, there were the industrial PMUs, which consists of 3 phases rather than 1 phase that Bogdan, Mike, Andy, and I are working on. So moving right along. So one way to analyze it is post-event analysis. There are 2 separate ways to do post-event analysis, one of which is doing sectional analysis. The power industry is a very volatile industry in regards to it gets very affected by weather. So the grid might be working fine one day and it starts raining and might not work the next day. So it's very important to sectionalize what's happening. For instance, if there's a thunderstorm in the lower part of Wisconsin, you want to look at the data in the lower part of Wisconsin. And what you can do, what I did here was access the PMU data from the Pi server and looked at the voltage waveforms. What's happening during this time? The voltage right here, is this the right laser pointer? That's actually a span of 7 days. We're looking at a generation pattern near a generator to see what's happening in the angle oscillation in terms of the Upper Peninsula. What that means is the angle oscillation just means that the grid is slowly unsyncing itself and coming back, unsyncing, coming back. And we want to figure out why that's happening. So we want to sectionalize, just look at that section only to figure out what's happening. Is it just the load that's moving around? Is it just the generation that's moving around? What do we need to build a new line across? Separate out the angle of it? These kind of things can be figured out by looking at sections.
What's the time scale on that display?
This is 24 hours. I mean, the whole thing is
Saturday, Sunday are the first 2?
Saturday, Sunday, yes. Then
No, the 2 peaks.
right here,
Saturday, Sunday, right?
I think I actually started off with Thursday. I was doing the analysis on Thursday.
Is this voltage?
This is phase angle, actually.
Phase. What is the scale on the left?
The scale should be, that's hard to read. I think it was at 30 degrees phase difference with respect to somewhere else in the grid.
But you're showing a whole week there?
Yes, a whole week. So this is in the beginning of the day, then end of the day, beginning of the day, end of the day, and so on and so forth. And just as an aside, you can usually when you look at these kind of data, you look at voltage magnitude when there is something like a thunderstorm, and when you have loads cutting off, like lines tripping, you usually look at phase angle.
What's this, the blue thing at
The blue thing on the bottom is the load I was looking at the time. This is a generator up in northern peninsula, Michigan. It's not actually Wisconsin. And
Call it the UP.
the UPU, yeah. What? Oh, really? Then the grid is not really stable up there. It's not very strong. There isn't many generators near the area. So there's always a huge angle separation. And I was trying to figure out what the cause of this was. And this is the conclusion I reached here. It's being caused by the generator nearby. Because there's only one generator nearby supplying the voltage, power. So it has to have a large angle difference in order to have the power transfer over. as if there were more power generators along the way, then it wouldn't be so large. So moving right along, there's the other one, the full territory analysis. Sometimes you don't really know what's happening just by looking at the section. If it's a more broad range of events happening, it's much better to look at the whole grid when you're analyzing this. This right here is a phase angle gradient that I scripted out of VBA. If anyone's familiar with it, it's a function within Excel. If you just go to the developer tab and just press that VBA script, you can start programming stuff. And what this did right here, I took a bunch of data points, the PMU data, extracted the PMU phase angle, and mapped it out throughout the grid. And by looking at it right now, at this grid, at this picture right here, you can tell that there's a high angle and a low angle. The way that I set it up, high angle would mean that energy is coming in. And low angle would be energy is being used. So you can tell that the UP is a fairly unstable area, as phase angle around the area is very steep, for lack of a better term. And
I can't say at this point, I
yes.
think it'd be useful to show us where the Great Lake is in this,
The-
outline Wisconsin, Michigan.
Okay, so
Obvious.
the Great Lake, here's Lake Michigan, right here. And up to here is roughly Wisconsin. And up here is the UP. And let's see. I'm not sure if I want to go too much into how this was programmed. I mean, the way this is programmed is just you take several points, 100 points within the grid, and to get the gradient across, I just did some estimation in between. It's almost like what Professor Yi Lu showed when she showed the analysis for the power outage a couple years back, actually from last year's presentation. So it's a replication of this. By using this and storing the data, you can actually play it back over time, meaning if you want to look at what happened on September 20th for a 24-hour period, you can play it back by looking at the data. And sometimes you can find that voltage phase angle swings, as in maybe caused by line trips somewhere else, or perhaps this phase angle went down and power stopped coming in. You can tell what's happening outside of the territory as well. So that's
I'll go back.
yes.
Now, one of the things I want to do is I want to sing Kent's praises on this, because he is totally responsible for that graph. It came to him as a blank piece of paper and said, please go create a graphical depiction of the phases. And so he had as intern to solve that problem. And he solved this problem in about 2 weeks' time.
A little more with with animation. That took a little bit more time, but roughly 2 weeks.
This is at one instant of time,
This is at one instant of time,
everything is all synchronized.
all synchronized. It's the way that PMU data works is, like Bogdan said, it's all synchronized to a GPS time clock. So we're pretty certain, up to in one microsecond, that they're all at the same time frame. And especially with the power grid being 60 hertz, it could move around a lot if it's not really accurate. So if it's accurate up to 1 millisecond, for instance, it might show a much different map of the phase angle since it shifts around so much. So moving right along, there's the real-time analysis. This is something, it's a work in progress. One of the things I did up there is a PMU status map. As the research about PMU data quality, synchrophaser data quality, one of the biggest concerns about PMUs is that they lose time sync, and they stop putting out reliable data. As in, depending on the vendor, it might be that voltage might go from 138 kV to 0 all of a sudden, and that might alarm it. So this status map right here shows the PMUs all across Wisconsin and the UP, roughly 100 PMUs in the ATC territory. And I have a legend over here. This tells that data flow is okay, data flow is fair, data flow is poor, and data is reliable or questionable. So there's two aspects we need to focus on. The way that PMUs work is you have a PMU and a PDC. A PDC takes all the data from a PMU and concentrates it in one place. If the data is retrieved properly from the let me repeat that. If the data actually goes to the PDC correctly, then the data flow is okay. If the data is showing lost time sync or some weird data, then there'll be unreliable data. So this map would actually show two things at once. You can see that things are transferred okay, and sometimes they're not. And across the grid, you can, I'm not sure if you can see it on here, probably not, but you can also tell reliability in data. I probably snapped it when I was blinking, so.
You're calling these PMUs, are they
Yes.
really the digital fault recorders that don't have anything better to do, so they give you PMU data as an aside bonus?
Can you rephrase that?
Well, maybe
The question is, are they all the same device? Same brand, name?
No, they are not. There's roughly 3 different types of PMUs out there. One's by Schweitzer, one's by Meditech, and I can't remember the last one.
Meditech is the DF, the digital
Yeah,
fault recorder.
yeah. So,
Yeah, 'cause that's all he makes,
right.
digital fault recorders. But he figured while he's recording nothing, he may as well make it into a PMU because there's no fault. It's just sitting there waiting for a fault to happen, and if there's no fault, it doesn't do anything. So he figured, I'll make it into a PMU. So that's some of them, I guess, right?
Right. I think, I'm not sure if I should say it, but around here is the Meditechs. But you can just say, we can keep that a secret there. And moving along, improvements to real-time analysis. So far, we can do post-event analysis and to see if the PMU is working or not. We don't actually do anything with the PMU real-time. So this is where the ATC, UIUC, and PNNL project comes in. We can use a statistical means to analyze the data and figure out what's happening real time. For instance, if a line trip occurs, there could be many different causes for it. It can be either a tree falling on it, lightning hitting it, or it could be hunting season and someone shoots one of the transformers down, which is completely plausible. So it might be one of those, but depending on the case, it'll have different behaviors on the voltage magnitude or the phase, most likely the magnitude first. So we can actually take a cloud of data, as in a mass amount of data, then categorize it into different behaviors. Behaviors during the day, behaviors during the night, behaviors during Saturdays, Sundays, so on and so forth. And from that, we can figure out if something is abnormal or not. And this is a project I'm working on with Carl, Dr. Hao Zhu, Jose, and Andy Yoon out there. One of the things we want to try to do is detect the cause of faults. So if we know the cause of faults, such as lightning, we can figure out what's happening during lightnings. We can also detect data quality issues. If it's showing a 0 out of nowhere, then most likely the PMU is not working at the time. So by implementing this, we can actually improve the grid performance. As in, we can either predict what's happening, as in right now, sorry, let me rephrase that part. SCADA right now only tells you if the line tripped or not. At Y22, line tripped, cause unknown. capacitor bank locked out, cause unknown. And you actually have to have someone else go there and check it out to figure out what's happening there. By having historical data to back it up, we can automatically set an alert for the cause. It could be a squirrel going into the capacitor bank, blowing up. Happened this summer. Like I said, hunting season, that's another one.
The hunter was really trying to get the squirrel.
It was actually a 17-year-old practicing shooting or something like that. Happened a couple years back, apparently. They didn't have the PMU data for that, unfortunately. Otherwise, I would have brought it here. But and by implementing this to run in real time, we could improve grid performance, as in we have a better understanding of the grid in real time, as opposed to right now, which has to wait for SCADA, which has a longer delay of a couple minutes, actually, as opposed to 2 seconds of PMUs. And I think that's all I have right now. Any questions, comments? Yes, Professor?
Yeah, that's a nice presentation. So on your internship, how was it different from what you expected?
Oh,
Was this your first internship?
yes.
Okay, so explain to the group how it was
You ran
different.
into a retared dean, right?
Yes, Dr. Rich Schultz. I ran into him. He was 10 steps away from me. I was in the cubicle. He actually had an office. He came in 3 times a week. But so I saw him a couple times.
So other than that, how was it?
Oh yeah.
Expected.
So actually, the internship was, I guess, I don't know what to say about it. I was expecting more. I was expecting more isolated. I guess a more lonely internship. But it turned out to be a pretty fun internship, as in people around me helped me out. I actually had another intern with me to work on another project, which was mapping out the RTU status. Driving to work every day was not so fun.
Where did you work at?
In Cottage Grove.
Okay,
From
brought it to WPL.
yeah. So
Who did you work for? Who's your boss?
Jim Kleitch, April Bakken. I gotta go up more. I can't remember my boss's name, but and no, it was a fun internship. Besides, like, there's always construction in Wisconsin, so sometimes you leave the office at 5:30, you get home at 7.
You had to drive to work right along that new transmission line, right? The one they put along the Beltway. What is that? West Middleton to Rockford or something?
I think it was something like that.
345 kV line.
It's the
Big tower.
it's the big octagonal towers, I think. I'm not quite sure, but
That caused a lot of controversy.
there was actually a presentation about that when we had our intern orientation. They talked about how all these transmission lines were built, and there were always some controversies, and they had to go around and convince people that we needed it. I mean, energy demand doesn't go down, so I guess it is a necessity, and you can't have things hang out.
Sure? You sure they have
Oh,
that?
ATC. I actually have the keychain holders right here. Yeah. Any other questions, comments, concerns? Did anything not make sense? I can go back and explain it.
Did you get to go up to the UP to see what you're talking
No,
about?
not quite. I got out to a substation in right by Pewaukee.
By where?
Pewaukee,
Oh, by Milwaukee.
but that's about it. It was a pretty big substation. It was really hot, especially no, it was I can't remember. Sorry, I can't get it off the top of my head. It's like 10 minutes away from the Pewaukee office. And nothing else here? All right, thanks everyone.